Okay. So just to remind you, if you ever look at this again, so we have a continuous load. So we're going to write one set of equations. And we cut it here at our arbitrary distance x. You can see either side, we're going to have to deal with a trapezoidal load system. Either side we have a reaction, so that's pretty even. But we'll go with the left side because the dimension will be a little easier to deal with. Everything will be x, x, x. This side would be 18 minus x. It just gets a little messier. So with that said, working the left side, I need to find my reactions at A. So I'll come over here and draw a free body diagram. And assume positive shear at A. And this is going to look weird, but positive shear at B. These are not reaction forces AY, BY. These are shear forces. Right? The left side positive is up. The right side positive is down. Okay? Just a little different way of looking at things. I've got, really the only thing I have to be concerned with now is this trapezoidal load, which has this 1 kip per foot on this side. And I'll hold off on that side right now because what I want to do is treat the trapezoid as two objects we're better equipped to deal with. A rectangle and a triangle. Now, what would be, we already know that the height of my rectangle is 1, so this value over here would be 1 kip per foot. The total height is 3. So that means the height of the triangular part would be 2 kips per foot. I don't know how many times I see on exams students say the height of the triangle is 3. Okay? So keep that separate. So now I'm going to have my force, concentrated equivalent force for my rectangular piece, which will be what? Oh, I'm sorry, I left off the dimension here. It'll be 18 times 1, right? 18 kips. And since I'm going to try to find the moment arm or the reaction at A, I'm probably going to sum my moments at B. So let's find the distance from B. What would that distance be?
9 feet.
Yeah, half the distance or 9 feet. Now I've got my concentrated equivalent force for the triangular part, which is 1/2 the base, 18, times the height, 2. So the 2's cancel, and interestingly enough, I get 18. And what is that distance? Well, from the high end, it's 1/3 the distance. 1/3 of 18 is 6. So with that done, I'm going to sum moments at B, and I'll have the two concentrated equivalent forces and then balanced by the reaction. Both of these forces create what kind of moment in my sign convention? Positive. Right? Right-hand rule. Positive about B. So I'll have the first one will be 18 kips times 6 feet plus 18 kips times, 9 feet.
I just so happens that they're the same.
That's just the way the numbers worked out. Right? This 18 kips is the area of the rectangle, which is 18 times 1. And then this 18 is the area of the triangle, which is 1/2 base 18 times height 2. So the half cancels the 2, and you get 1 times 18. And then I have my shear force at A, which creates negative moment with the moment arm of 18. So what is my shear at A equal to? Looks like 6, looks like 15. Is that okay? That one just worked out very nicely. all the 18s cancel, and you just get 6 plus 9. All right, so now I'm ready to do my free body diagram. Let's come back over here and look at the free body diagram of this left-hand side. I'm going to try to draw it a little bigger than normal to give us some room to put all the pieces in. So I'm still cutting it at X. I now know my shear at A is 15 kips. And then I have this triangular load, which starts off as 1 kip per foot, right? What is the value here? What's the slope of this line? If I go back and calculate the slope, what do I get? What's the change in the height? 3 minus 1 is 2 over 18. So that's a slope of 1 to 9. So that means I'm going to start off at 1, and this is a 1 to 9 slope. So that means this value should be 1 plus x over 9. Right? You're going to start at 1, and you're going to add how far you go. 1/9. Now you can check that. When x is 0, what do you get? 1. That matches. When x is 18, you should get 3. And you get 18 over 9 is 2, plus 1, 3. So it checks. I'm going to go ahead and indicate that I'm going to break this up into a rectangular force and a triangular force. And I'll write these in different colors so you can see it. So I know the rectangle is still 1. So what's this little additional piece? It's going to just be x over 9. 1 plus x over 9 equals 1 plus x over 9. So I'll have two forces. I don't have much room here, so I'll just call this force 1 and force 2. So what is the value of force 1? What would be the area of the rectangle, which is 1 times x, that's just x. Force 2 is the area of the triangle, which is 1/2 base x times height x over 9. So that becomes x squared over 18. Okay? And then we would have d1 and d2. d1 is equal to half the distance, x over 2. d2 is equal to 1/3 the distance, so that would be x over 3. So you can see this particular one has not complicated, but a pretty, complicated. Pretty complicated free body diagram. So you can see, if you do all your work there carefully and take your time, then the rest should come out pretty clean. So let's see what happens. Oh, I forgot to put in the important things. Positive shear, positive bending moment. The things we're actually trying to find. Okay, so let's do that. So let's sum the moments using right-hand rules, our sign convention, at the cut surface. Make sure they're in equilibrium. So let's account for all the moment here about the cut. So at first we have the internal moment M, which is positive. Force 1 and force 2, what kind of moment did they create about the cut? Positive or negative? Positive. So let's do 1 first. So force 1 is x with the moment arm of x over 2. Force 2 is x squared over 18 with the moment arm of x over 3. And then I have my 15 kip reaction force. That creates positive or negative moment? negative. So I have 15 times the moment arm of x. So now my moment, which should be a function of x, is equal to, so I'm going to throw all these terms to the other side of the equation. We'll start with the highest order term. So I'll have negative x cubed over 54, that's this term, minus x squared over 2, that's this term, plus 15x. And that should be kip feet. Think that's good? Well, we know some things. What's the moment at x equal to 0? At a pin. Better be 0. Put in x equals 0, 0, 0, 0. That checks. What is the moment at x equal 18? A roller. What's the moment at a roller? 0. Put in x equal 18. What do you get? It might take you a minute to do that one. I can't do cube roots in my head. Or I have a feeling that it's going to be 0. But I want you to check it. Anybody get 0? Miss Holland's got it. Anybody else? Everybody else is still going at it. Yep. Okay. I like that. Isn't that great? It's like these problems when they just check themselves. All right. So the last thing we need to do is we'll sum the forces in the y direction to find our shear. So starting over the left side, I've got my shear force acting down. F1 is acting down. F2 is acting down. And my 15 kip force is up. So shear as a function of x looks like it's going to be minus x squared over 18 minus x plus 15. And that should have the units of kips. Now, do we know the shear at x equals 0? What is the shear at A? We found it. It's 15. And does our equation give us 15 at x equals 0?
Yes.
It does. Now, what is the shear at x equal 18? Now, we didn't find our shear at B, but if you put in x equal 18 here, what do you get? I think you get 21. But you go ahead and check. Yeah, you get negative 21, right? And if you went up here and actually solved for this, you would find out that you would shear at B would be negative 21. So I think that's good. And last, say again.
Negative 21.
Are you not getting that? You should get 36 plus 15, or negative 36 plus 15. Isn't that 21? Okay.
0. I thought it was 10. I got you.
Now,
Right.
What about the last one? Does the derivative of the moment with respect to x equal the shear? I think if you check it, you'll see that it does. So we got everything in this problem. And the great thing we got is now that we have an equation. So where would the moment be maximum in this beam? I have an equation for moment. How do you find the maximum value of an equation? What do? Take the derivative and set it equal to?
0.
What's the derivative of the moment? Shear. So I just have to find where the shear is 0. It's a quadratic equation, but I think you could probably do that. You could set the shear equal to 0 and find a value of x. That would tell you where the moment is maximum, and then you could put that x value back into the equation and actually tell me the maximum moment to be. That's pretty useful. So any other questions before I close this one down? Okay.